We have already discussed the concept of encoders. Today we will discuss about decoders. Okay. Actually, uh, this logic circuit or decoder, it converts n-bit binary input code, n-bit binary input code into m output lines such that only one output line is activated for each one of the possible combinations of inputs. Okay. Here we have a set of inputs. 2 raised to n input codes will be there. These n codes are given as input to decoder, and we have a set of outputs in which only one will be activated. Say we have d0, d1, d2, etc. up to dn minus 2, dn minus 1, and out of which only one output is high for each input code. Okay. Since each of the n inputs can be 0 or a 1, there are 2 raised to n possible input combinations or codes. For each of these input combinations, only one of m outputs will be active or high. All other outputs will remain inactive or low state. Okay, this is a logic circuit. Here we have the decoder circuit. Here we have 2 raised to n inputs or n inputs in general. Input codes will be 2 raised to n and m outputs, and here only one will be active for each input code. Listening to the theory section, it may not be that much easy for you to understand, but when we discuss about the design phase, when we discuss the design of each decoder circuits, it will be clear to you. Okay, for the time being, just understand that this is an n bit. There will be n input binary codes, n bit binary codes, and at the same time we'll have a set of outputs, and from that only one will be active based on and the remaining sections will be what we call inactive. Okay, please go through. I have already drawn the figure of our next topic, 3-line to 8-line decoder. The thing is that once we have learned the concepts that we have already learned, that is multiplexer, demultiplexer, or topics related to that, we already know the concept of how we can construct the truth table and the corresponding figure. Okay, 3-line to 8-line decoder means here the number of inputs will be n. Number of inputs n is 3, and also the outputs corresponding to this will be obviously 2 raised to 3, that is 8. And decoder says that, or the concept of decoder is that out of those 8 outputs, only one will be active at a particular time. Okay, so this is the concept that we have followed here also. 3-line to 8-line decoder means we have given 3 inputs A, B and C, and based on those inputs we have constructed 8 outputs. That is, it's already 3-line to 8-line decoder. 2 raised to 3, 8. Okay, so what we have done here is, when we have 3 inputs, the corresponding combinations will be definitely from 0, 0, 0 to 1, 1, 1. So based on that, when we construct this truth table, we understand that actually what we do is, when the 3 inputs A, B and C are all zeros, we give the concept that, or we should say that we have constructed like that in such a way that D0, 0, 0, 0 means it's 0, right? So it's constructed in such a way that when both these, all these 3 inputs A, B and C are zeros, we say that D0 is 1, or D0 is 1 means D0 is the only case where it is active. Okay, as told in the what we call the definition of decoder, there are actually 8 outputs. That is, 3-line to decoder contains 3 inputs and 8 outputs, but out of this 8 output, just one is active at a time. Okay, so when all these inputs are zeros, so A, B, C, it goes for corresponding value is 0, right? we can understand like that. Okay, we can calculate or we can study like that. So in that case, D0 is the only one active, so we have put a 1 here. 001 means D1 is active, so we have put a 1 in D1 position. 010 is 2, so we have put the value 1 here, and we get in diagonal shape we get the values 1, right? So how can, based on this case, how can we construct the left position? If in you are looking at textbooks and all, you may find a different figure, but as I told before, in the case of demultiplexers or multiplexers, the best thing is go for ABC, the 3 inputs, and the corresponding what we call the negation part. Okay. First of all, we can go in any manner. I have taken the order D0 to D7 to D0. We can take the other way also. Okay. D0 to D7, like that also we can take. It's up to you to decide. Okay. But based on these inputs, we are going to construct it. Okay, so the order is D7 to D0. So A, B, C. You can also go for that the other case like this. Okay, if you want, but this is also possible, as I told in the earlier classes. Okay, A, B, and C. Okay, when both these are positive, that is 1, 1, 1. D7 is positive, so D7 is equal to ABC. Here, next one is A, B, C bar. A, B, C bar means it stands for D6, so D6 is A, B, C bar. Like that, we construct all these cases. Let me check. A is positive, B is negative, C is positive. A is positive, B is negative, C is negative. A bar, B, C, and A bar, B, C bar, A bar, B bar, C, and this is A bar, B bar, and C bar. Okay, likewise we construct all these cases. Clear? Please. One more thing I like to add in this particular topic is 3-line to 8-line decoder is also called binary to octal decoder. Okay, binary to octal, because it takes 3 binary inputs and we get the corresponding octal, and out of which only one is active. Okay. Then one is binary to octal decoder, and another name is 1 of 8 decoder. 1 of 8. How this particular decoder got this name means out of these 8 outputs only one is active at a time. So this can also be called, how this name came means 3-line to 8-line means we have 3 inputs, and based on that we have 8 outputs. 1 of 8 means out of 8 octal, it's another name. Okay, out of 8 octal cases we have one active case. And binary to octal means we give 3 inputs as binary, 3 input binary, and we get the corresponding octal, and out of which one is active. Okay, clear? Before we go into the next design, I would like to bring your attention to just 2 topics. I'm not going for the design and all, just to introduce 2 concepts. Okay, 2 cases. Enable inputs will be seen in the next design onwards also, but this is just a mention about BCD to decimal decoder. Okay, mention about. Okay, enable inputs. Sometimes decoders may contain more to 2 or more, at least 1 or more enable inputs. Okay, enable inputs means, for example, in the previous example we have seen 3 inputs, right? A, B, C. It was in the case of 3-bit 3-bit to 8-bit decoder, right? Okay. in the case of ABC was the 3 inputs. You can understand that all those 3 inputs, that is A, B and C, determined which output is to be get activated. For example, when A, B and C held the value 0, 0, 0, the output was D0, right? So it was solely based on ABC or the input, we determined the values or the output in that particular case. Okay, so I am going to introduce to you the next topic or the next case, that is enable inputs. Enable inputs means sometimes the decoder may contain one or more enable inputs. The enable input actually is fed as an extra input to the circuits. Say for example, I think now it's clear to you. Okay, if you are taking B and A bar, this enable will be fed as the third input. Clear? So it will be fed to the third input, fed as the third input to the gate. Okay. You know what is the significance of enable input? Actually, in the previous case, we found that when we have 3 inputs, A, B and C, the output came from AND gates. AND gates. I think you remember that. From the AND gate, we took the value as D7 is equal to ABC likewise, right? So, some people might get a doubt that if it was, why we took AND gate? Actually, we designed a active high case, okay? Active high case. When it is active high, we go for AND gate. We need to understand that, okay? When we go for active high circuits, we go for AND gate, and when it is active low circuits, we take NAND gate. You know what's the difference, right? When we draw AND gate like this, NAND will be exactly the opposite, right? With a bubble. Okay, that is, understand that if we are going for an active high circuit, we need to go for AND gate, and if it's an active low circuit, we need to go for NAND gate. Okay. So when we introduce enable to along with the inputs ABC or simply AB, actually enable will determine whether the output should be there or not. That is, actually enable pin is an extra pin that is added along with the gates, and enable from here on solely determines whether to be active or not. Okay, if we have an active high case, we are going to develop an active high case, and based on for example, I will give you another example. Okay, we are going for an active high case, and here the enable pin is also high, and based on high enable pin, what we got, we have 2 inputs A and B, and we get a result, right, based on the input AB. Okay, but in the case of if in case the enable is a low case, we are going to design the high case, but enable pin is low. Whatever be the values of A and B, whatever be the value of A and B, the whole system remains in active low state. That is, this enable pin solely determines whether the system should be active or not. That's the significance of enable pin. Okay, it will be clear when we go for the next design. And BCD to decimal decoder means here we have 4 inputs, okay, but we have only 10 outputs. I think we have understood why 10 outputs, right? That is, in the case of BCD, we have only 0 to 9 cases. Okay, so inputs will be 4 and 0 to 9 will be active. That is, 10 states will be active, and the rest of the cases will be inactive. Clear? Rest of the cases will be inactive. Okay, and in the case of if we have adding and enable, sorry, for the time being, forget about enable. In this case, if the whatever be the values of inputs, the invalid states, that is when we count 0 to 9 and 10 to 15, these cases will still remain as invalid. Clear? Forget about that enable part. We have 4 inputs and we have 10 outputs, and those invalid cases 10 to 15 will remain invalid whatever be the values of the inputs. Clear? Okay. Next topic is 2-line to 4-line decoder using Nand gates. As I have told before, when we see a question like using Nand gates, or when we see a question like using convert it into logic, or what we call in logic low state. Okay, in such cases we should go for Nand gate. Okay, if it can be they can specify using Nand gates. Okay, or otherwise construct the circuit in active low state. In such case also we go for Nand gates. Okay, so using Nand gates means we should have a logic low state. So in such cases what we do is we go for the enable pin. Enable. Okay, so 2-line means we go for 2 inputs. Okay, and another one B. Okay, A and B, 2 lines. And to 4-line means definitely there will be 4 outputs, right? Okay, once one minute. Okay, then we need to have an enable pin. Okay, so as I told in previously, when enable pin is there, and whether the value, if for example we are going to construct an active low case, and based on that, enable pin will determine or solely take the control of both those inputs, and it's based on enable that we determine the output or the system will work or not. Okay, so when enable is equal to 0, in this case it is active low case. Active low means the system will work. And when enable is equal to 1, there are 2 conditions. When enable is equal to 1, as I told in her previous class also, when we see a bar in a particular figure, it means that it becomes active only when we get a 0 on that particular position. And if it's E and we give a 1 means it's not active low state. Okay, this enable pin will get activated only when it receives value 0. Clear? Okay, so when enable is equal to 0, it will work, and enable is equal to 1 means it won't work. Okay, so we have an enable pin. In textbooks and all, you may find a figure like this. Okay, this is actually, some people may get confused in this particular case. Okay, I will draw, and I explain where this confusion occurs. We will draw 4 NAND gates. Okay, and we are going to go for the truth table. Okay. Truth table. We have enable A, B, and yes, D0, D1, D2, D3. Here also we write D0, D1, D2, D3. Okay. Our next case is, okay, here it's active low case NAND gate is used. So when it's 1, it's our assumption, okay, we can interchange the value of 1 and 0, but we for the ease of design, what we say is, if we see a 0, it's the active low case and it should work, and if it's 1, it won't work. Okay, so when enable is equal to 1 means it's the reverse case. So whatever be the values of A and B, whatever be the value of A and B, so I have written X there. It can be zeros, it can be ones, no issues, because it's enabled and it's in active high state. We are going to design an active low state. So here enable is equal to 1. So all these cases will be 1. 1 means here it's active low. In the previous case, when we designed the 3 line to 8 line case, what we saw is we received 1 in diagonal position, right? Okay. In that case, it was active high case. So we should receive 1 values. Okay. And here this is active low state. So enable is equal to 1. Value of X and B can be anything. And here we need to receive the value 0 as its active low case. Okay, but this is active high, all these cases will be 1. When enable is equal to 0, based on these cases, we have 0, 0, 0, 1, 1, 0, 1, 1. Right? Okay, enable is high means, one second. Enable is 0 means it's going to be active low, so this particular system will work. Okay, 0, and based on this we need to receive outputs. Okay, 0, 0 means we need to receive 0 here because it's active low. 0, 1 means we will receive 0 in D1. D2 means here 0. D3 means again 0. Okay, and the rest of the values will have 1. I will repeat once again. When we are going to construct active low case or using NAND gates, in such case enable should have value 0 in order to make it active low. Okay. In that case, if it's 1, whatever be the values of A and B, we say that the output will be 1. Output will be 1 means as we are going to design an active low case, the output we should receive should be 0. And enable pins, enable values are zeros and corresponding 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, and based on that we receive zeros in diagonal position and the rest of the values will be 1. Clear? And about the confusion part, in such a case we need not draw it. Okay. Confusion part means when we receive, actually in some textbooks we see that there is a NOT gate. In some textbooks there won't be any NOT gate. They will be drawing a figure just like this. Okay. and connecting to the corresponding gates. Okay. The thing is, some people have a tendency to go for conversions here. Okay, go for conversions means in textbooks, when E is equal to 0, the system becomes active, and when E is equal to 1, the system become inactive. This is already given in the truth table. See, when E is equal to 1, it's inactive state, no output is received. When E is equal to 0, the system is active and we get the output, right? So, some people have a tendency to give the E values here and convert it, as there is NOT gate. Some people may convert it and they give the value 1. So, when E is equal to 1, it becomes inactive state. Such people may get confused and make a lot of mistakes here. So the best thing you need to understand is, this figure can be drawn with a straight line, or a NOT gate can be given. It's according to us. In many textbooks you may find that it's us who decide whether E is equal to 0 and it becomes inactive. It becomes active. When E is equal to 1, it becomes inactive. It's us who decide. Okay, we need to decide. We can give any values. Okay, but for the simplicity, I would say the best thing is we need to receive zeros in diagonal positions. Okay, so what we do is, as it's active low case, we need to have a NAND gate, and when enable is equal to 1, we say that the system is inactive, and when enable is equal to 1, we say that the system is active. So here what we do is, don't go for when E is equal to 0, it's active, don't go for conversions. Okay, just assume that this value that we are going to give, that is enable 0, in all these cases we need to give an enable. So what we need to do is give an input directly to it, and this value 1 case is not at all included. This is the best thing to avoid confusions. Okay, don't go for unnecessary confusions in this particular case. Okay, and we have an A here, and A bar, and we have a B bar, and we have again A bar, and here we have a B. Okay, here we have A, here we have B bar, here we have A, here we have B. Okay, rest of the values, if you want, you can rub it off. Clear? Let me check. Yes, this is the answer. I repeat, don't go for conversions here. Assume that if you give a straight line and write there enabled, no issues. Okay, so the best thing is, don't go for conversions. As we have received the question as using NAND gate, we assume that it's going to be active low state. I repeat, okay, active low state. In active low, we say that the system becomes active only when E receives 0 value. So it works only in when the value E is 0. 1 value means whatever be the values of A and B, we receive no output. Here it's active low, so we need to get the output as zeros. That's why we receive zeros here. Clear? Our next topic, 4 to 16 decoder from 2, 3 to 8 decoders. Okay, when we get such a question, the first thing that should come to our mind is, we are going to design a 4 to 16 decoder, right? In previously also we have seen such topics. In such design in previous topics as well. Please go through when you get time. Okay. 4 to 16 decoder from 2, 3 to 8 means there will be 4 inputs. Okay, that fourth input, that should be the first logic. Okay, that fourth input should be fed to two different circuits, same as in previous topics. Okay, here also we did the same. A0, A1, A2, A0, A1, A2 will be common for both these two 3 to 8 decoders. Okay, these two cases, and we have an A3, the fourth pin, that is given to the NOT gate for inverting and fed, and this is directly fed to the next case. Okay, how it works means, actually when the value of A3 is equal to 0, when the value of A3 is 0, we give the input, an inverter is placed in front of that particular case, so it becomes 1, and this first decoder becomes active or becomes enabled, this is disabled. Okay, and but the value of A3 here was 0, right? It is fed, it becomes 1 and it becomes enabled, so this particular case is enabled and the second circuit produces only zeros. Okay, this is the case we have produced here. Okay, A3 is 0 and the different combinations of A0, A1, A2 we have written like this. Okay, so 0, 1, 1, 1 means D7, 0, the D0, D1, D2, D3, D4, D5, D6, D7. Till this will be controlled by the first case, so it becomes the 3 to 8 decoder, first 3 to 8 decoder. And the 0 when fed to this particular case produces only zeros. Okay, and in the next case, when A3 produces value 1, it becomes 0 and this particular decoder becomes disabled and this is enabled. Okay, when this is enabled, this produces only outputs zeros and this particular case produces the result D8 to D15. Okay, that is the value of A3 here was equal to 1. It is fed directly. Okay, 1, 0, 0, 0. Then the values of A0, A1, A2 will be those combinations 0, 0, 0 to 1, 1, 1. You know, we have seen such designs previously, but the thing is, after the operations of all these values 0, 0, 1, 1, 1, definitely it becomes 1, 0, 0, 0. That is, the value of A3 is equal to 1, or we have learned that when we consider that ordinary binary case, 7 is represented by 0, 1, 1, 1 and 8 is represented as 1, 0, 0, 0. 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, right? This is the same procedure that we follow, and this produces only zeros, and this case, when A3 is equal to 1, this becomes enabled and produces the result D8 to D15. Okay, this is how we create 4 to 16 decoder from 2, 3 to 8 decoders. Okay, this is a circuit.